As I mentioned earlier, chapter 6, we're only going to cover 3 sections. However, they are fairly important. And in fact, the stuff that we're going to do today is almost guaranteed to show up on a free response question. It'll make more sense when we get there, but every year that I've been doing AP Calc, this type of problem has shown up on the test. So if you can get this under control, it's not a difficult subject, but if you can get it under control, guaranteed at least 6 points on one of the problems, because it's not real tough stuff. And you'll see more examples of this when we get into actual practicing with AP questions. But we're going to do differential equations. We've done differential equations already. The concept is fairly simple. We have a derivative, and we want to go from a derivative back to a function, which you would also know as an integral. And the integral is an important part of taking a differential equation. And we're also going to finally talk about slope fields today. It's something that keeps popping up, but we ignored it, but we're going to talk about slope fields, which is also a fairly easy thing to do. Okay, so you should be able to go from initial conditions to a particular solution. We talked about taking a differential equation and finding a family of solutions that would have a plus c on the end of it versus a particular solution, no plus c, just one particular answer. We'll talk about slope fields, and of course you should be able to drive a stick shift car. Can anybody not? Most people can? We should have a field trip then. I love teaching people to drive stick shift.
It's brutal.
It's tough. I learned on a hill. Yeah. My mom got out of the car, put the parking brake on, and said, "You're driving." On a hill. First time ever drive a stick shift on a hill. All right, so blah, 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 blah. I talked about this already. We're going to go, this whole process is called the differential equation. We're going to go from a general solution to a particular solution. And we have to have some information in order to find that C term, which gives us the particular solution. So we're going to start with this type of example. These pop up every once in a while. They're not that earth-shatteringly important, but they are something that we need to talk about. So we have this differential equation here. Y double prime minus y equals 0. I would like to know which, if any, of these equations satisfies that differential equation. Does that question make sense? Okay. So for instance, in part A, we have y. What's y double prime?
Negative sign.
Who said that? Jesse, how'd you get that?
Because if you take the derivative, it's cosine, and then.
Okay, so we'll do that too, just so everybody can keep up with us. Yeah.
And then derivative again, you'd get negative sign because, yeah.
Okay. So does it satisfy the differential equation? Well, we know what y double prime is. Negative sine of x minus y, which is sine of x. Does that equal 0? No, doesn't work. Okay. Let's move on to B. I think I got some space on the next slide here. So let's go here and jump over here. So that doesn't work. What about B? You do that one. In case you didn't copy it down in time, it is y double prime minus y equal, minus y equals 0. We're wondering if that satisfies, if y equals 4e to the negative x satisfies the differential equation. Yeah, it's cold now. I did, it's gone. Where's it from? Warner Brothers? Margaret the Martian. I don't want to talk about it. It's not helping. Okay, what's y prime? Well, first of all, what's the answer? Yes or no?
No.
Well, that didn't go as planned. Yes or no? How many think it's yes? How many think it's no? How many don't have a clue? Good. Okay, this could be fun. What's y prime? Negative 4 e to the negative x. Why, Casey? Yes, you could do product rule. There's nothing wrong with that. You could do product rule. It's just more work than you need to do.
Well, yeah, I thought, didn't she say?
Go ahead.
She said,
Did you say not a clue or product?
oh, I said.
You said product rule.
I thought you said not.
I thought you said not a clue.
Thank you.
Okay, first one times the derivative of second plus first one times.
So what's the derivative of e to the negative x?
The negative x times
Good. Itself times the derivative of the exponent. What's y double prime? Does it satisfy the conditions?
Yes.
4e to the negative x minus 4e to the negative x. Does that equal 0? Yep. So it satisfies the differential equation. And then one more. ce to the x. What's the derivative of ce to the x? And what's the derivative of ce to the negative x, or to the x? So the first derivative is ce to the x. What's the second derivative? And the third derivative? Are we seeing a pattern here?
Yeah.
So it's second derivative minus the original function, yes or no?
Yes.
Yes, it works. So it works for any value of c. Because again, the derivative of e to the x is itself. First type of problem, does it satisfy the differential equation? Not earth-shatteringly important. What's more important is this stuff. So I have some derivative, dy over dx. We're not using y primes here. It's important that we do it as dy dx. You'll see why in a second. Equals 2x cubed minus 3x. Okay, well, what does this mean? That means that there's some function y that when I take the derivative of y, I get this, right? How do I find that function? The integral, good. But now that we're officially doing what's called a differential equation, there's a couple extra things you need to throw in. So first things first, we have to do this. This is called separating the differentials. These guys, the dy and the dx, are the differentials. We have to separate those differentials. This is the single most important step in the problem. Every time this type of problem is shown up on the AP test, it's worth anywhere from 4 to 6 of the 9 points. However, every grading rubric I've ever seen has one simple note. If they don't separate the differentials, it's a 0. So please remember to separate the differentials. Now, why do we have to separate the differentials? Why can't I just come here and say, okay, well, I want to take the integral of that and the integral of that? What's wrong with that?
That's the integral of y over x, and then you don't have a dx to notify that it's x is a variable.
Perfect. Couldn't say it better. Did y'all hear him?
No.
Try again.
Did you hear him?
I did hear.
Alright, so on the left, it's becomes y over x.
Well, regardless of what it becomes. Go ahead.
If you take the integral, it's y over x, and then on the right, you don't have a dx to define that x is the
Is it? Variable.
yeah, variable.
Okay. So way back when we started learning about integrals, I said that dx is really important, or that dy or that dz, whatever variable we're working with. Some of you have gotten very sloppy with it, but you see why it's important. By splitting this up, we're now saying that this side of the function is involved with a y, this side of the function is involved with an x. So it's identifying what our variable is. Then, once we separate the differentials, then we can take the derivative. Or sorry, take the integral. That's a legal move, integrate both sides. This will be fun. What's the antiderivative of dy? Y. What's the antiderivative of 2x cubed minus 3x?
1/2 x to the 4th minus 3/2 x squared.
Plus c.
Plus c. They would both have a plus c, but we don't need to because it's an indefinite interval.
No, that's not.
Y
That
plus
was
c.
Plus C question?
Like that on the left, it's going to be y plus c.
Question mark.
because it's an indefinite integral.
So I was
Y,
asking-
comma,
that's what I was
plus
asking.
C question mark.
Okay,
Yeah.
Oh, not
Yeah.
WHY. You're not asking why is it that there's a plus C? You're asking if the left side is Y plus C.
Is that what you meant when you said?
Yes, but we don't need two C's. If I have a plus C on one side and a plus C on the other side, what's C minus C?
Other C value.
C, correct, not 0. So the rule of thumb is you always attach the C to the X stuff so that we keep it nice and pretty in a function notation. So nothing new here. We've done integrals before. We understand going from a derivative to a function, getting a general solution, that's fine. This is the important step here, separating those differentials. You have to do that. Because again, you need a dx and a dy. Do not cost yourself 6 points out of 9 because you forget to move a little dx to the other side. Oh boy. Okay. Now, if we wanted to find a particular solution, I would need some initial conditions. I would need to know which function or what point lies on the function so that I can find C. In this case, I'm not going to find C. I'm just going to stay with that general solution. Whoops, little itchy trigger finger there. What are we doing? Slope fields. Okay, so finally we find out what slope fields are. Read that while I pass out a worksheet.
Shut up.
Still don't like it.
Come on.
Come on, Belvo.
Come on down. You can get it.
Okay, so let's go back to this problem. After we solve the differential equation, we have a general equation. So what could C be? Anything. Could be 2. Okay? So if it's 2, we would get a curve, correct? Yes or no? Yeah. So what if I change C? What if instead of 2 I make it 10? You get a different curve. If I make it negative 100, you get a different curve. You could graph all those curves on a coordinate plane, but it would be a mess. So what slope fields do is instead of graphing the functions, we graph the slopes of those curves. So here's the first one we're going to work with. This is not the function, this is the derivative. So to do a slope field, once you see the process, you'll see that number 1, it can be fairly tedious, but number 2, it's not that difficult. I have some curve or some function, and when I take the derivative of it, I get x minus 1. Okay. So what if x is 0? What's the slope? Not even 0. Let's go 0, 0. We'll go to the origin. At 0, 0, what's the slope of the curve? Sorry, what's the slope of the tangent line to the curve? Negative 1. Why?
Plug in 0.
Plug in 0. 0 minus 1 is negative 1. So I have some curve, regardless of what it looks like, the slope of the tangent line at 0, 0 would be the line negative 1. Instead of drawing the entire line in here, I just draw a little dash. And you approximate that slope of being about negative 1. Okay, negative 1 meaning it's slanted this way and it's at 45 degrees. Let's go up to, let's pick another random point. Let's go up here to 0, 1, 2, 3, 0, 3. What's the slope of the tangent line to the curve at 0, 3? Negative 1. Part of slope fields is being able to make recognize patterns and make a generalization. What's going to be true about all the slopes on the y-axis?
It's gonna be
Negative 1. And they get a little sloppy as we move around, but that's okay. Let's try something else. Let's move over here. What's the slope of, in case you didn't see that, I'm at 2, 0. What's the slope of the tangent line at 2, 0?
1.
1, because 2 minus 1 is 2. Sorry, it's 1. I'll teach you calculus.
Bless you.
Without continuing to plug and chug, let's make a generalization about all those values. What's going to happen?
They're all gonna be 1.
They're all going to be 1. Now let's split the difference. What if x is 1?
0.
0. Let's go to the right. What if x is 3?
2.
2. So now, this isn't an exact science, but we want our dashes to be steeper than the 1. So you just make it a little steeper. And again, it's not a exact science, we're just ballparking. What happens when I move over further? It keeps getting steeper and steeper. What happens if I go back the other way?
Same thing. in
Yeah,
reverse.
steeper in the negative direction. Good.
Not like slope fields.
If you look at those slope fields, that gives you the shape of all the possible curves that satisfy this condition. What shape does it appear to be? A parabola. Does that make sense? What kind of function
Yeah.
is this?
Yeah. Quadratic.
This is a quadratic?
A line.
That's a line. And what happens when you integrate a line? It becomes a parabola or a quadratic. Okay. So the slope field represents all the possible functions or slopes that could be generated from that derivative. But then the next step is, what happens if we want to look at a particular solution? Come on. There we go. So at the point 2, 1, I want to draw the curve, that one particular curve that goes through that point. And again, this isn't exact science, this is where you ballpark it. So it's going to look something like, it's going to curve that way and go up, and then it's going to be level down here, and it's going to hit there, and curve up like that. Whoops. You get something like that. There's the particular solution. Yes, sir.
How do you know it doesn't come down to 1, 0?
It might, but again, I'm ballparking it.
Okay.
I know that at that point, because at 1, all of it has to level out. So regardless of where I draw the curve, it's got to have a minimum there at that point. Okay. Next step would then be to do the differential equation and solve for that function. Okay, so let's do that. First things first, separate the differentials. Next step, integrate. Okay, we're good because each integral has a differential attached to it. What's the integral of dy?
Y plus C.
Y plus c, but for our purposes, just y. What's the integral of this? What's it?
Plus C. No, minus X plus C.
Okay, so here's our, this equation represents all those little dashes all over the graph. How do I get the blue graph? Well, I plug in 2 and 1 and solve for c, and then I would have a particular solution. Okay? On your worksheet, things change a little bit. Let me get rid of this. And get rid of this. Let's do one that has both an x and a y in it. Let's take a look at the one in the lower, number 3. Negative x over y. Looking at that derivative, what's going to cause some problems?
The Y.
What about the y?
Can't be 0.
When y equals 0. So y can't be equal to 0. Where's y equals 0? X-axis. So therefore, there will be nothing on the x-axis because it has no slope. So this is going to stay blank. By the way, do you have any idea what kind of differential equation, what's our graph going to look like when we're done? All right, we'll find out. Here we go. What about, so this we skip. Let's go here. At 0, 1, what's the slope?
0.
0. 0, 2, 0, and 0, 0, 0, 0, 0, 0, 0, 0, 0. We're not going to fill in the whole thing. We'll just wing it. Can't do 1, 0. But what about 1, 1? Negative 1. So let's see if we get a pattern like we did last time. What happens if I move over to 1, 2? Negative 1/2, so it changes, which means negative 1/2 is going to be a little less steep. What about 1, 3?
Less steep.
A little less steep. And it's going to continue to level out as you get further and further up. We can extend that going downward now. This would be positive 1, and then a little less steep as we go down. If we flip to the other side of the y-axis, it'll be easier to see. What about the point negative 1, 1? 1. And then going up, it gets a little less steep. This one will fill in like this, and you start to see the patterns there that emerge. What shape does that look like?
Circle.
It's a circle, right? If you do the differential equation for this problem, you will get a circle. X squared plus y squared equals r squared. Okay. So it's literally just plugging points into the derivative and drawing little dashes representing the slope of all of those lines. Yeah.
Do you have to do like a whole box or just?
No,
one to
because
each?
you'd go crazy. There's like 4,000 of them, and then, yeah. Okay. Any problems with that? Okay, so again, the dashes represent all the possible solutions. When we start looking at going through a particular point, then we start looking at a particular equation. And you'll be doing both, the slope field to generate the entire picture, and then particular solutions to put that curve through there. So for instance, I did a particular curve in this one through the point 3, 3, no, 2, 2, sorry. I would get a circle that looks something like that. Again, trying to match up the slopes as you get closer and closer to it. Okay, we good? Beautiful. Get rid of that. Back here. Get rid of that. Oh, look, it's a slope. Okay. All right, we're all done with that.